Hello guys, and welcome to another calculus video. This one is going to be a really fun one. I have here this awesome, amazing integral that we're going to solve today. I got from a friend 3 incredibly tough integrals recently, and this is one of them. I've solved one other one, and so we're going to be doing a video on that too. This is honestly one of the most incredibly difficult integrals that I've done in my integrating career, so to speak. So let's jump right into the video, and I hope you guys enjoy. So first, let's talk about some identities that we're going to be using. First off, in my last video on Glasser's master theorem, I proved the following identity, that the integral from 0 to infinity of 1 over x to the fourth plus bx squared plus a, or I guess actually it was ax squared plus b, so let me fix that. It's ax squared plus b dx is equal to pi times b to the negative 3 over 4 over 2 square root 2 plus a over square root b. So we're going to be using this. So we're going to have the integral from 0 to pi over 4 of square root tangent x times square root 1 minus tangent x dx. So we're going to start with the obvious substitution, u equals tangent x. And then we're going to have inverse tangent of u equals x, or dx equals 1 over u squared plus 1 du. So we'll have integral from 0 to 1, square root u, square root 1 minus u, over 1 plus u squared du. Now in order to get rid of those nasty square roots on the top, we're going to make the substitution u equals sine squared of theta. And du is going to equal 2 sine theta cosine theta d theta. So we will have the integral from 0 to pi over 2 now. So this is essentially making the substitution tangent x equals sine squared of theta, just through two separate substitutions because that was kind of hard to see. So now we're going to have square root of sine squared of theta is just sine of theta on this domain, and then we're also going to have a cosine theta from this 1 minus u right here. And then we're going to be multiplying by 2 sine cosine theta because of our differential, so that's that. On the bottom, we're just going to have 1 plus sine to the fourth of theta. Now, to get rid of this sine to the fourth, since sine is sometimes a little bit more difficult to deal with, we're going to multiply by secant to the fourth on the top and bottom. So we're going to have the integral from 0 to pi over 2 of 2 times tangent squared of theta. Cosine squared of theta is just going to disappear. And on the bottom, we're going to have secant to the fourth of theta plus tangent to the fourth of theta, d theta. Now I'm going to go ahead and reorganize this a little bit. Instead of tangent squared of theta, we're going to rewrite this as secant squared of theta plus 1 and split it up into two different integrals. So 2 secant squared of theta plus the integral from 0 to pi over 2 of 2 over secant to the fourth plus tangent to the fourth, same thing over here, right? On both of these integrals, we're going to make the substitution tangent theta equals u, and then, or I guess I shouldn't use u since I used that before. Let's go ahead and use v. That means that dv is going to be secant squared theta d theta, or dv equals v squared plus 1 d theta. So on this leftmost integral, we're just going to have the integral from 0 to infinity of 2 over, now remember that secant squared theta equals v squared plus 1 because of how tangent works, so we're going to have v squared plus 1 squared plus v to the fourth dv. And on this one over here, we don't have secant squared theta on the top, so we're going to just have integral from 0 to infinity of 2 over v squared plus 1, v squared plus, and then this same thing that we have over here, v squared plus 1 squared plus v to the fourth dv. All right, let's go ahead and make some more space. So let's go ahead and expand out our v squared plus 1 squared plus v to the fourth. So once we get that, this is just going to become 2v to the fourth plus 2v squared plus 1. All right. So now you can go ahead and notice that this is just a representation of our formula that we proved in our Glasser's master theorem video. So we can go ahead and divide by 2 on the top and bottom here. This is going to become 1/2. And using our formula, this integral, this on the left here, is equal to, alright, so our b is going to be 1/2, so we have b to the negative 3/4, which is going to be just 2 to the 3/4 pi over 2, so that's going to end up just being 2 to the negative 1/4. And then we're going to be dividing by square root 2 plus a over square root b, which is just going to be square root 2. So that's the first part of our answer. And now we're also going to have to deal with this nasty bit over here. So let's go ahead and write this in as well. So 2v to the 4th plus 2v squared plus 1. Now, in order to make this a little bit simpler, let's go ahead and try and get rid of this v squared plus 1 right here. So one way that we can do this is we're going to sub v equals 1 over alpha. Then that means that dv is going to be negative 1 over alpha squared d alpha. So once we get the substitution, I'll just call this part I1, and we're going to solve for I1. So I equals 2 to the negative 1/4 pi over square root 2 plus square root 2 times plus I1. Okay, so once we make this substitution, we're going to have that I1, our bounds are going to end up being the same since they get flipped, but then we're going to use this negative sign right here to put them back. So we'll have the integral from 0 to infinity of 2 times 1 over alpha squared over 1 plus 1 over alpha squared times 2 over alpha to the 4th plus 2 over alpha squared plus 1. Now let's go ahead and multiply this alpha squared in right there. So we're going to just get alpha squared plus 1 on the bottom here. And if we multiply by alpha to the 4th on the top and bottom, we're going to get just an alpha to the 4th up here. And here we're just going to get, again, alpha to the 4th, alpha to the 4th plus 2 alpha squared plus 2. So we kind of flipped everything around there. Now, we want to go ahead and simplify this, right? This is all d alpha. And I see here that I have this alpha to the 4th, and I also have an alpha to the 4th down here. So if I can maybe make this top look like the bottom, maybe I can simplify things a little bit. So if I go ahead and add plus 2 alpha squared plus 2, and then I also subtract minus 2 alpha squared minus 2, we're going to get end up splitting up into 2 separate integrals. So we're going to get I1 equals integral from 0 to infinity. Oh, this was all 2. So I guess I should be making this should all be 4s. So for this first part right here, this is going to cancel with this, and so we're just going to end up with 2 over alpha squared plus 1 d alpha. And for this separate part, this is actually going to cancel with this, so we're going to end up subtracting integral from 0 to infinity. Oh, I'm sorry guys, I just noticed something from before. I said that tangent squared x equals secant squared x plus 1, but really it's the other way around. It's secant squared x minus 1. So we should actually be subtracting this entire integral over here. So this is going to be minus I1 right here rather than plus I1. Let's go ahead and fix that. Sorry about that, guys. That may have been a little bit confusing for some of you, but gladly I caught my mistake before it was too late. Okay, and so we're going to cancel this off, so we're going to be subtracting 4 over the integral of alpha to the 4th plus 2 alpha squared plus 2 d alpha. And let's just go ahead and make some more space. So this first integral on the left is just super easy. It's going to just be equal to pi after using arctangent. And we're going to be subtracting this other integral, which can be solved using our integral formula that we derived in the last video again. So we're going to be subtracting 4 times, and then we're going to have b to the negative 3/4, and in this case b is just 2. So we're going to have 2 to the negative 3/4. And then we're going to have pi, and we're going to divide by 2. So on the top, you can just make this a 2. And 2 times 2 to the negative 3/4 is just 2 to the 1/4. And then we're going to have square root 2 plus a over square root b, I believe. And so that's going to be 2 over square root 2, so we're just going to have square root 2 again. And so this is our answer for I1, and when we combine our total answer, we're going to have pi times 2 to the 1/4 minus 2 to the negative 1/4, or sorry, plus 2 to the negative 1/4 over square root 2 plus square root 2 minus 1. This is also equal to pi times 2 cosh of ln2 over 4 over square root 2 plus square root 2 minus 1, which I just think is a cooler way to write it. So this is our integral. Overall, I think this is definitely probably in the top 5 toughest integrals that I've ever solved. You know, dozens of hours of works actually went into solving this integral. Maybe not dozens, but you know, at least 6 or 7 hours of work went into just grinding out different methods and trying to figure out a way to actually evaluate it. So I appreciate you guys if you watched through the whole video. I hope you guys enjoyed the solution to this quite epic, monstrous integral that we were able to solve. Yeah, I hope you guys enjoyed the video, and I'll see you next time for another amazing integral.